chapter for energy changes, is it an easy topic? Definitely not. There's actually a few particular concepts here that are really important. So later on, what we're going to do is we're going to first go through the content, of course, right? To talk about what are certain things we need to look out for, certain things that we need to know. But right after that, I'll prefer to put majority of our focus on trying the questions and then using that as a chance to go back to certain concepts. Now, this chapter is not one of the chapters where you can just study and memorize. You really have to see how the questions are being tested, the concepts, and how they would try to turn it into a question. And then from there, you can then better check your understanding level. Okay. So once again, this is a chapter that we need to understand a few important things, but it will be the questions that will make the most difference. Now, let's talk about some of the most common questions you will see in energy changes. But before we go on, we need to talk about some of the more important basic foundational stuff. Let's begin with understanding the difference between exothermic and an endothermic reaction. For this, I want to bring up two keywords, and I need you to write down these two keywords with me. The first keyword I want you to write down is the word system. The second keyword I need you to be writing down is the word surrounding. Now, the reason why I'm making you do this is because your choice of your keyword here is really important. Now, when we talk about system, the correct keyword that's attached to system is the energy level of the system. This has nothing to do with endo or exothermic. So every time we're talking about the system is referring to the energy level. And when you're looking at the surrounding, we are thinking of the surrounding temperature. Now, what exactly is the difference between system and surrounding? System consists of your reactants plus your product. It is the chemical reaction itself. So when a chemical reaction takes place, the energy level of your chemical reaction can either increase or decrease. So this is related to energy level. So if I highlight this word energy level, this is the energy level that we're talking about. But when we're talking about surrounding are things that are surrounding the chemical reaction. The surrounding is passive, they do not react. When we use the word surrounding, we're referring to your surrounding temperature. What you need to remember here is that the system and the surrounding are related. Now, let's talk about an exothermic reaction to start. An exothermic reaction is one whereby heat energy is released from the system into the surrounding. I always say the easiest way to visualize an exothermic reaction is like a dragon spitting out fire. So the dragon's own energy level, his own system, his own energy level will drop. But when you spit out fire, you cause the surrounding temperature to increase. Therefore, an exothermic reaction will cause the surrounding temperature to go up, but the own system, which means the reactants and the product, their own energy level will decrease. This is typical of reactions like combustion, neutralization, respiration, condensation, and freezing. Okay, so you need to understand the relationship between system and surrounding. Endothermic reaction, on the other hand, is the reverse. We're actually taking in heat from the surrounding into the system. So your surrounding temperature will actually decrease. So everything now is at a lower temperature, right? It's colder. Where did all this heat energy go? All of this heat energy went into the system, causing the system's energy level to increase. The system's energy level is also commonly represented with this thing called delta H. This refers to the enthalpy change. In an exothermic reaction, because heat energy is leaving the system, your enthalpy change here would be a negative value because you're releasing, so your own energy level will end up dropping. On the other hand, for endothermic reaction, because the enthalpy change here is positive, it's more of like because you're absorbing heat energy into your system, that's why your enthalpy change is positive. This is largely for reactions such as dissolving of salts, thermal decomposition, photosynthesis, or electrolysis. I'll say a common point that you can notice across this is that energy is absorbed. For photosynthesis, we absorb light energy. For thermal decomposition, we absorb heat energy. If there's an inflow of energy from the surrounding into the system, that is what we'll consider an endothermic reaction. Okay, so what we are really focusing on here is getting our foundation right, making sure you know the difference between exothermic and endothermic. These will be two keywords that we will be constantly coming back to. Okay, so just remember, system refers to the chemical reaction itself. We always talk about the energy level of your system, right? If your system releases heat energy like a combustion reaction, you're exothermic because you're releasing heat energy, causing the surrounding temperature to increase. In an endothermic reaction, your system is absorbing all the heat energy, right? So it's taking in heat energy. That will cause the surrounding temperature to decrease. One common misconception that a lot of people have is that they tend to think that the system and the surrounding is the same thing. And that becomes a problem. Why? Because when you do so, you will start realizing that a lot of things starts getting very complicated. You start confusing yourself. How so? You think that, oh, system heat energy release, then you're like, oh, how does the temperature change? No, you need to think of energy level and temperature as two separate things. That is your best shot at making sure you do not confuse yourself for this chapter. Later on, we'll talk about some of the techniques that I've outlined here, including how to do some of the conversion. Now, what is more important is you understand how an energy level and energy profile diagram works. Sorry, this one, you just help me rename it a bit. This is a bit more accurate if we call it the energy profile diagram. So what the energy profile diagram shows you, okay, is this curve. There's a few pointers that we need to take note of. The first thing that you must make sure that you do is to label the axis, energy level, and take note, the x-axis is not time. The x-axis is progress of reaction. Now, if you ask me why that's the case, because the entire reaction takes place over a few seconds. So if you were to draw this over time in seconds, the entire graph will be like very small. It only take place over a few seconds. But if you say take place over the progress of the reaction, then it will showcase over the entire duration from start to finish. So progress of reaction is more accurate. The next thing that you need to do is to label in all of the reactants and product as per your balance equation. So if your equation is a combustion reaction, you label it in, write it down as per a balance equation. Okay, if it's decomposition of water, you can also write that down. So this one is literally copy paste from the question. You just write down the reactants and the products after. The last thing that you need to do is actually to go and label your arrows. So for activation energy will always be an upward arrow. There's no room for debate here. Okay, so activation energy is easily understood as the starting point to the highest point. So this is where I started. To get to the highest point, the mountain that I have to climb, what's the height of that mountain? That is your activation energy. So same for this, obviously the mountain's a lot taller. So you can see here that the activation energy is more. So activation energy, you can think of it as the height of the mountain you have to climb. So it depends on where you start and how tall the mountain is. On the other hand, enthalpy change would depend on the scenario. If you're dealing with an exothermic reaction, you'll get a negative enthalpy change because the energy level of your system is decreasing, as in an exothermic reaction, heat energy is released. However, for endothermic reaction, as heat energy is being absorbed into the system, we would see that the enthalpy change here would be a positive value because the system's energy level is increasing. So you need to label this with the arrows. I think that's really important. All right. And that is how you draw the energy profile diagram for exo and endothermic reactions. Okay, up next, let's move on. The last most common question type that you're going to get is one that discusses about bond energy. So for bond energy, this is largely calculation based. There's also a few answering technique. If we have time, we'll go into it. So the trick here for bond energy, I always simplify it down to an equation that looks like that. This is the same one that I teach my own students. Enthalpy change is equivalent to the bond breaking minus all the bond forming. Now, let me go into detail. What exactly is bond breaking? Bond breaking means when you start off with a compound, for example, CH4, you are trying to break all of the bonds that are in this molecule. So all of this CH bond, we're going to break them. Now, what do we break in a reaction? Remember, you always break your reactants. I'll say that the easiest way to remember this is that reactants are like the raw ingredient that you are bringing to the kitchen, right? You need to chop up all your ingredient. So for the reactant, you have a CH4 here, right? It's going to chop it up all into smaller bits. So you always break all the bonds of the reactants. Meanwhile, for bond forming is putting them together to form bonds. You always form the bonds of your products. In other words, a typical question would involve you calculating the number and the different types of bond in your reactants. You're going to be breaking all of those bonds. Okay, and then you're going to subtract all of the bond forming that you do for your product. Like I say, this one, sure, we can talk to you tomorrow about how it works, okay? But more importantly is when you get a question, do you know what to do? So later on, we're going to take a look at a couple of questions. Then we're going to come back and apply this concept. So that's the reason why I'm rushing through some of this, because they are all better understood once you start doing questions. Okay, so let me move on for bond breaking, bond forming. We'll come back to this for sure. We can also choose to use a catalyst. When we do so, I want you to notice that in the past, the mountain was really tall. But when you do it with a catalyst will reduce the activation energy by providing an alternative pathway. So it becomes easier for us to react compared to before, which translates to more reaction, which translates to a higher rate of reaction. So a question can be as simple as they give you the initial energy profile diagram, and they ask you to sketch in what happens if you add in a catalyst. When you add in a catalyst, the activation energy will decrease. Okay, so the key thing here is understanding that a catalyst will lower the activation energy. Okay, this one here will be related to the following lesson that we're covering, which is under rate of reaction. Okay, so energy changes and rate of reaction are related to one another. The remaining stuff like combustion and hydrogen fuel cell, combustion is pretty straightforward. If it's a complete combustion, you should be getting CO2 and water. But if it's an incomplete combustion, meaning there's insufficient oxygen, you'll end up getting carbon monoxide and water. All right, I think it's very important for us to be labeling down incomplete combustion will occur if there is insufficient oxygen. Meaning we do not have enough oxygen to burn everything to get complete combustion. Complete combustion means there is excess oxygen. There's too much. I cannot use finish. All right, so when we are burning anything, we need to make sure that there is enough airflow for oxygen to come in. Otherwise, you'll end up in a situation where it becomes incomplete combustion. Alamak, I should have annotated on the other diagram. However, it's too late. Okay, so like I said, right, what we're going to do is we're going to focus more on doing questions. I would say that the questions is the best way for us to check for our concept understanding. So I'm going to give you guys around a minute to try question 1. If you're not confident, I highly suggest you go back, right, to the notes, all right, to refer, to see if you can remember the difference between system and surrounding. That will be one of the key things in order to get question 1 correct. Okay, so just 1 minute. After that, actually, can the 3 of you, since there's only a small group today, right? Can you just type in the answer in the chat once you have your answer? Then that way it's easier for me to know if you guys are done. Okay, we start with question 1 first. So we're dealing with an endothermic reaction. Okay, seems like all of us here, we managed to get the answer pretty fast, right? We talked about how endothermic reaction, all right, energy would be taken in. So it will be taken in from the surrounding into the system. This will cause our energy of our system to increase. As heat energy is taken in from the surrounding, the temperature of the surrounding will decrease. All right, so I'll say this is one of the simplest questions you can possibly get in an exam. So I'm glad that you guys got it right, which goes on to tell me that your foundation is somewhat pretty good. Okay, so there are no issue, which means we can safely move on to question 2. So let's give ourselves a chance to try question 2. For this, I'll give you a solid 2 minutes. Okay, 30 more seconds. Okay, seem like your answers are in. So let's take a look. Okay, seem like most of you did get the answer here this time around. So good job. Yes, answer here is D. But I don't just want to talk about why the answer is D. I think it's equally as important for us to look through and understand why A, B, or C is wrong. Okay, so I want to take a look at option A first. In an endothermic reaction, less energy is absorbed in bond breaking than released in bond forming. Now, I want to go back to something that we talked about earlier. So going back over here, I mentioned this idea of how we will always be thinking of how bond breaking and bond forming is related. To calculate how our enthalpy change is being affected is always by taking bond breaking minus bond forming. Now, how is this relevant to this question that we're doing over here? In an endothermic reaction, I need you to know that your enthalpy change should be a positive value. So this over here, the enthalpy change should end up becoming a positive value. If you want to get a positive value, your bond breaking must be bigger than your bond forming. So that after subtraction, you will still end up with a positive value. So in an endothermic reaction should have more energy absorbed for bond breaking than is released during bond forming. Bond breaking value should be bigger than bond forming. Okay, that's what's wrong with statement A. Next, statement B, in an endothermic reaction, the activation energy is always higher than in an exothermic reaction. Now, let's explore the validity of this statement. Now, if you take a look at an energy profile diagram like we have over here, I want you to notice that it is true that when you just compare 1-to-1, endothermic reaction tend to have a larger activation energy. if you're comparing between two similar reactions, these two are not similar reactions, by the way. I'm just saying hypothetically, if you're looking at a reversible reaction, right, the endothermic one will always have more activation energy than the exothermic one. The keyword here that is off, right, is the word always. Would the activation energy always be higher? No. The activation energy of an endothermic reaction is usually higher than that of an exothermic reaction. But in chemistry, if we use the word always or all, it's referring to a sweeping statement where it's mentioning that everything, like it's a rule, everything will obey this. That is not true. There are specific endothermic reactions while the activation energy is actually lesser than an exothermic reaction. So that is why statement B is incorrect. It's not that it's not true. It is true most of the time, but not all of the time. Okay, so when you see the word always, you want to be careful in the exam because always means every single time. Okay, and it's trying to say that there are no exceptions. All right, and that is not true. There are exceptions to the scenario. Lastly, for C, what is wrong? For an exothermic reaction, I want you to approach this in the reverse manner. We understand that enthalpy change is BB minus BF. And in an exothermic reaction, you should expect a negative enthalpy change because heat energy is being released from the system. So in this scenario here, your bond breaking should be smaller than your bond forming. Okay, so here the statement that is wrong is the word more. It's supposed to be less energy is absorbed in bond breaking. Can? So very important for us, yes, to make sure we get the question correct, but it's equally as important, right, to understand why the other options are wrong. Statement D is true because in an exothermic reaction, if we were to sketch out the energy profile diagram, I want you to notice how the energy level of where your reactants are at is always higher than where your products will be. This is always going to be true. Okay. If there are no further questions, we'll move on to the next one in question 3. Okay, for this one, I'll give you all a solid 1.5 minutes to attempt. Then we're going to proceed from there. We're going to do very fast, yeah. I love it. But take your time. You still have another 30 seconds. Hey, okay. All answers are in. This is a bit challenging, right? Okay, let's check the answer together. Answer here is actually D. So I see a couple of you actually choose B. All right. And that's fine. That's fine. But I think it's more important for us to understand why which one is exo or which one is endo. Now, I want you to focus on the first stage first. I need you all to see that what is happening here is that I'm taking the hydrogen and the oxygen. I take out my knife and I freaking go and chop it up. I break the H2 into individual hydrogen atoms. I break my oxygen into individual oxygen hydrogen from molecule to atoms. This process is known as bond breaking. Right? So I break my diatomic molecules into individual atoms. And bond breaking, just to be clear, is it exothermic or endothermic reaction? Bond breaking is endothermic. Now, how do we know bond breaking is endothermic? I just need you to have this very simple visualization. If you want to break a bond, for example, you want to go and chop vegetable, right? I need you to imagine that it's endothermic because you need to use energy. Okay, so you need to absorb energy into the system so that you have enough energy to break the bonds. If you want to think of this as a endothermic as very cold, right? You can think of the cooking example that I give. You know, when you want to cook, you need to go and chop the ingredients, right? When you first take out the vegetable from the fridge, it is cold. So when you're trying to prepare ingredient, I want you to imagine that all your ingredients are still quite cold because you just take it out from the fridge. So that itself, we call it bond breaking. So bond breaking is endothermic. So you can use a bit of a mental picture in your head. Imagine touching all the vegetables that are cold, right? So cold means endothermic. All right, temperature decreases. So bond breaking is a process that is endothermic. Okay, so stage 1 is definitely not exo. Now, in stage 2, I want you to see that the individual hydrogen and oxygen atoms are actually coming together to form water. This stage is known as bond forming. And bond forming is exothermic. Now that you're done chopping up all of your ingredients, you're putting them together and you're putting it in a frying pan, right? Then you start stir frying it. You finally get your final product, the dish that you're looking for. During the cooking process, remember you need to use fire is hot. It is exothermic. So I want you to think of bond breaking and bond forming as we always bond break the reactants. The ingredients preparation, we chop it up, that is bond breaking, right? You just take it out from the fridge, it's still cold. Bond forming, on the other hand, is when your ingredients are all chopped up already, you throw it into the frying pan and you stir fry it together. You will form the final product, which is water in this case. And because you're throwing it in a frying pan, it's hot, there's flame, we can think of it as exothermic. So with that, it becomes easier for us to remember that bond breaking is endo, bond forming is exothermic. Just think of yourself in the kitchen cooking a meal, right? I would say that will make it more easy to memorize than how you would traditionally just try to hardcore memorizing it, right? So this is called studying smart, right? You associate it with a process that you know, and then you can visualize, the temperature, how it changes as you're preparing ingredient versus when you're cooking. I would say that will make it easier for us to remember that bond forming here is exothermic. Lastly, as I turn from a gas to a liquid, this is actually condensation. In case you're wondering, condensation is actually an exothermic process. If you're not too confident, you can always refer back to the notes, all right, which is why it's included here. I want you to see how condensation is an exothermic process. So condensation and freezing are both processes where heat energy is being released. Okay. Meanwhile, you can add in here if you want to, melting and boiling. These are endothermic processes. Can? All right. So over here, we can say that 2 and 3, these two processes are exothermic. So that is how we will approach this question. Not the easiest, but I would say attemptable. That means next time when you try, okay, you should have a better chance attempting it. Okay, let's move on to the next question over here. Let's take a look at question 4. Same thing, I will give you all 2 minutes. Not the easiest, they're asking for the reverse reaction. Okay, seems like you all have the answer on this. So let's take a look at question 4. Seems like all of us gotten the answer here, which is C. So fantastic. But more importantly, how do we make sure that we are all on the same page? Because I don't want you to get the answer, then later it's by luck. Anyway, right, if you're being smart about this, right, the activation energy will never be a negative value. Remember earlier, I always say it is the height of the mountain you have to climb. It will always be upwards. So there will never be a scenario, right, where it will be a negative value. And this leaves you with only two choices, either 30 or 40. Now, in the original uncatalyzed reaction, if you draw in a dotted line here, I want you to see that the uncatalyzed reaction was from 50 to 30. This means that the original activation energy that is uncatalyzed is a plus 20. But the moment you add in the catalyst, it will now become plus 10. But this is not the question, right? Because the question is asking us for the activation energy of the reverse catalyzed reaction. Okay, so what do we mean by reverse catalyzed reaction? It means that this entire diagram, we are just redrawing it again, but in reverse, which means instead of starting at Wx, we're starting at 10, and we're starting with Yz. So some reactions are reversible, for example, your Haber process. So this is just another way of looking at the situation, which means now it's reversed. It will still go up all the way to 50. Before coming back down and finishing off at 30. But this is for the uncatalyzed reaction. If we catalyze it, I want you to see that the height of the slope only goes up to 40. So the uncatalyzed reaction will look something more like that. It will only go until 40 before coming back. Right, and then we can write in the product, where product being W plus X. So the activation energy of the catalyzed reaction is from 40 to 1, right? The height of the hill that you need to climb. So from 40 to 10, the height of the hill is plus 30. So the activation energy of the catalyzed reaction is plus 30 kilojoule. All right, and if you have time, I will give you maybe just a minute to copy this down for those of you who want to. I think this is a very good way for us to understand what is going on. Okay, then for those of you who are done, we can start moving on to the next question. Okay, we'll be taking a short break at around 9:20, just to maybe go for a quick toilet break and stuff. After that, we'll come back and we'll push on to try more questions. Okay, so let's move on next to question 5. This one is an important question solely because it's been tested so much. Okay, but I'll tell you exactly how we will be doing this. But I want you all to try first. Yuying, you should know how to solve this, right? I hope so. Hey, Wang Kang is here. What's up? So Wang Kang, right now we're doing question 5. You can go and download the worksheet first. Okay, then we're gonna continue from here. Okay, so today is energy changes. Okay, another 30 seconds for those who are still trying. Okay, the reason why I'm giving a time limit is because in a typical MCQ, 40 MCQ, you have 60 minutes. So that is actually the scope of the paper. So on average, you have 1.5 minutes per question. Of course, some will be easier, which leaves you around 2 minutes for the harder questions. So we're always going to go with either 1.5 to 2 minutes per question. Okay, seems like some of us managed to get the answer here. Okay, answer here should be A. Yeah? Now, I think it's very important for us to make sure that when we do our calculations, right, we know exactly how it works. Okay, now for this one here, let me double check if there is any. Okay, I want to do the calculation alongside you, but it does look a bit weird at first glance. But never mind. Maybe there's a typo. I'll go and check on it later. But the correct way to be solving this question, first thing I need you to notice is the units for enthalpy change. This enthalpy change here is kilojoule per mole. Meaning if I actually burn 1 mole of methane, I'll get negative 880 kilojoules. If I burn 1 mole of ethanol, it will be negative 1380, so on and so forth. But the question here is not about burning 1 mole, we are only burning 1 gram. So the key working that you need to do here is to change this 1 gram into mole, followed by multiplying with the enthalpy change. Now, how do we do the working? Let's do it one by one. For methane, I need you to remember that mole can easily be found if you simply take mass divided by MR. So for methane, we only have 1 gram of methane and the MR is 16. So my number of mole is 1 over 16. Right, this is the number of mole. 1 mole will give me 880, but if I only have 1 over 16 mole, I will take 880 times 1 over 16. For the rest, I think you can sort of see what is the steps already, right? We can take 1 gram divided by 46. We can take 1 gram divided by 44. And of course, we can take 1 gram divided by 100. By taking mass over MR, you'll be getting the mole. And all you need to do is to take mole times the enthalpy change per mole. And that will get you the enthalpy change itself. So everything here, I'll just times 1 over 46 times 1 over 44, which is the equivalent of dividing by. So this one, to put it another way, is divide by 16, divided by 46, divided by 44, and divided by 100. Okay, so when you get all the values, the one that will give you the most energy, all right, which means the biggest value, should be the one where you take 880 divided by 16. If I'm not wrong, the typo here is that this one over here is supposed to have another 0. But let me just double confirm to make sure that that's the case. All right, let's just type it into the calculator. If I'm not wrong here, this one is 55 kilojoule. 1380 divided by 46. Down here is 30 kilojoule. 220 divided by 44. This one's a bit suspicious, but whatever. I'm just going to write 5. Okay, let me just... I think this one is a bit more realistic. This one, let's add in another 0. Doesn't really make sense for it to be 220. Okay, so let's go with the assumption it's a typo. Lastly, 4800, we divide it by 100. This one actually I don't even need a calculator. It's 48 kilojoule. Okay, so in other words, I think there is no doubt here that the one that produces the most energy is methane. All right, in 1 gram of methane, it produces 55 kilojoules. I'm going to use this chance, right, to quickly go back to the notes. And I want you to see earlier, I mentioned that we're going to talk about this, right? How do we convert kilojoule per mole to kilojoule per gram. That's essentially what we have done. And all you need to do is to times 1 over mR. The easier way to remember this, all right, is just remember you are technically just dividing by mR to turn it to kilojoule per gram. If you're not of the preference of memorizing, and I think that's perfectly fine, I would say that the way I approached it was I just think that I have 1 gram of the fuel. 1 gram is equivalent to how many mole? Once I find the mole, I take mole times kilojoule per mole to find the energy produced. You get what I mean? So I just imagine I got 1 gram, no? Then I change that 1 gram to mole. Then from there, I will successfully completed my conversion. So I actually prefer the working that I've shown you here because I think it's easier to understand, assuming your foundation in mole concept is somewhat decent. Can? So in a way, we are just dividing by mR. Okay, then you're just going to add in another 0 here. I think that will make a lot more sense. Hey, John is here. Hello. Okay, if not, let's take a pause here. Let's go for like a solid 5-minute break. And when we come back, we'll obviously continue to push on from question 6 onwards. Okay, so let's go for a short break first. I need to go toilet. Okay, be right back. How any of y'all watching SEA Games? I have some friends playing the SEA Games. So exciting. Let's go and watch the Mobile Legends SEA Games. Oh my god. Okay, for those of you in the chat, in the call, can y'all just give me a thumbs up or something if you're back? If everybody is back, we can continue. Yes. Tung 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 tung. Oh yeah, seems like everybody's back. Nice. Let's go. Okay, next question. Oh shit, I showed you the answer already. Oops. Question 6. Maybe I'll just give you a minute because it's a true, false, correct, wrong question. Yeah, I better start recording first. How? What's the answer for question 6? Wow, Nico, very fast. Okay, 30 more seconds for those who are still thinking. Gwen, fair question, but I will address that later. Okay, answer for question 6 is B. All right, so let me address each statement one by one. Statement A, this statement is not true because of the word only, produced by burning fuels. Not only. Yes, it's true that when we burn fuels, we do produce heat energy. We do get an exothermic reaction. But please understand that that's not the only way we can produce heat energy, right? There are other ways, such as things like change in state, even things like neutralization, heat energy is produced. So to say that it's only produced by the combustion of fuel is not true. It's not only produced, okay? So statement A is true, it's just that it's not the only way. Statement B is correct because hydrogen itself is a fuel, but the problem is hydrogen as a gas is very difficult to transport and store. You can actually find this in the notes if we go back up. There's this very short portion at the bottom where we're talking about the hydrogen fuel cell. So the pros and cons of a hydrogen fuel cell, one of the bad downside to it is that it's very difficult to transport and store. All right, so that is why while hydrogen serves as a viable option as a fuel, is not that commonly used yet. Okay, now methane is a good fuel because it produces only water. Not true. When you burn methane, a combustion reaction will produce both water as well as carbon dioxide gas. So CO2 and water. All right, that's what's wrong with statement C. D, do we need to know? D is just not true. Uranium is actually a metal. We do not burn metal and air to produce energy. If anything, you'll be burning a fuel, right? Or even possibly alcohol to burn it to produce energy. We do not burn metals for energy. So this is not true. Okay, so that's all for question 6. Let's quickly move on to question 7. Make sure you go and download the worksheet. If you want to print it out ahead of time, it's actually a good idea too. But today, my bad, because I didn't really upload it on time. In the future, it should be uploaded ahead of time. It was ready already, but we just forgot to upload. Sorry, got a lot of worksheets to upload. So this one is very similar to the previous question, which is what is always true of all combustion reaction? That should be quite easy, right? This one, if you know, you know. Good. So 3 of you send in your answers already. What about for John, Gwen? John, what do you think? Probably did this chapter in school already, right? Okay, I think all of us got it right. This one I'll go through a little bit faster. So what is true of all example is definitely that all combustion reactions are definitely exothermic reactions. There is no doubt about that. Okay, so this is always going to be true. Now let's quickly explore what is wrong with the remaining statement. Is the product always going to be carbon dioxide? Not necessary. It will be carbon dioxide if you are burning a hydrocarbon and it's a complete combustion. There is a good chance you might produce carbon monoxide as well, right? If it's incomplete combustion. So there is no guarantee it's always going to be CO2. Okay, can be carbon monoxide. What is wrong with C? During combustion as an exothermic reaction, the products should have less energy compared to the original. If you think about this in the form of energy, like principle of conservation of energy for my physics kids, when you are burning something and you release heat energy, it means that the energy conversion went from chemical potential to heat energy. So there's no way that the original fuel and oxygen versus the product have more energy. Impossible. It will always have less. Okay, and during combustion reaction, there would be bond breaking as well as bond forming. You break your reactants, you form your product. Okay, so no bonds are being broken, bullshit, right? Chemical reaction, always, the reactants will be broken. Let's move on next to question 8. This is almost the same as the previous question that we did. So if you could do the previous question, there's a very high chance you should be able to get it right. Okay, I want you to apply the same technique you tried earlier over here to see if you can get it. Okay, they're asking for activation energy for the reverse reaction. Okay, for those of you who are good with this, you might not even need to redraw it. You can do the calculation straight away, but no shame if you need to redraw because it will not take you that long anyway. So go ahead to redraw if you feel the need to. But if you can go ahead to calculate, why not, right? Save time. Okay, 30 more seconds for those who are still trying. Okay, let's go through. So answer over here is D. So good job to the 4 of you that got it right. But more importantly, how do we solve this question? The first thing I need you to know by now is that activation energy is the height of the mountain that you need to climb, right? Which means it will never be a negative value. Straight away throw that out. You have narrowed down your options to either C or D. Now let's explore why the answer is D. For me, I would go with the redrawing technique, meaning I would choose to redraw this entire circuit. I know that now if I reverse it, this is where my start point is, right? And my start point is a 2 and 2O. I will still go back up to the same height and I'll end off at where I am over here. So that means the height is still the same, right? The highest point is still the same. And I'm ending off at where I used to start. And this is where my 2N2 plus O2 is found. Now, it's very important for us to be labeling in the values because this is at the end of the day a calculation sort of thing. Now, the enthalpy change used to be positive 164. The new enthalpy change for the reverse is now a negative 164. The 164 gap is still the same. But more importantly, I need you to understand that the activation energy is no longer 447, but is from where you're starting to the highest point. This is the activation energy. Okay, so if you look at it, where is the activation energy corresponding to? If you take 447 minus 164, you'll actually get the activation energy plus 283. It's just the math of it. If you look at the height that I'm talking about, this whole thing is 447. This is 164. So when you take 447 minus 164, you'll get this height. This is the activation energy for the reverse reaction. The forward reaction's activation energy is 447. Okay, so that's why the answer here is plus 283. Okay, this is actually quite a common question in prelim nowadays, which is why we included it twice in this worksheet to make sure that you get the hang of it. All right, don't be the blur sotong and it's like, oh, this one's so easy, you know. Just look at this. No, it's for the reverse. So you need to flip the graph around. And this is how you do it. So I'll stay on here for another 30 seconds for those who are still copying. I think this is a very good correction to be doing because even in the future, you want to make sure you know how to solve this question. Okay, for those who are like very clear about this, you can start working on the next question already. Nobody's stopping you. Okay, you can proceed first. Okay, I know majority of you probably do not have time to be completing this worksheet before class. Okay, so usually for myself, I always try to make sure I give you enough time to try the question in class, and then I'll go through immediately. I find that to be like the most like fast way of learning. Okay, of course you can do it beforehand, good lah, but you know, like, hey man, we busy people, right? Okay, so you can do it in class, no worry. For this one, I'll give you all 1 minute to try. It's a pretty straightforward question. Okay, right. Answer here is just very clear cut, right? This one, answer is just C lor. So the height of the mountain that you need to climb from where you start to the highest point, this is activation energy. A bit lazy to write in lah. I think can you all tell me what does Z represent? You all type in the chat. So yes, if X represents the activation energy, then in this diagram, what is Z? It's a bit of a trick question, but think about it. Ah, Gwen, very good. So smart, so smart. If the rest then give up, not trying. Okay, so Z is activation energy, but by right, if you're talking about for this reaction, the enthalpy change supposed to be here. It's a positive enthalpy change. This is an endothermic reaction. So what Z is representing is actually still activation energy, but for the reverse reaction. Okay, but it's more for the reverse. So if we go down the other way, that means if we go this way, then that would show you the enthalpy change. You get it? So if you say Z is enthalpy change, is not fully correct. Z is the enthalpy change, but it's for the reverse reaction. Okay, let's move on. Let's move on to question 10. Wow, this one very fast. Okay, seems like you guys pretty much got the answer. So let's try for question 10. Answer is D, yeah? Yes. Okay, so activation energy for the forward reaction, all right, is the distance from where you started, all right, to the highest point. So this will represent your activation energy, labeled as energy activation. So if you take E3 minus E2, you'll end up with the activation energy. Bonus question, how do you get the enthalpy change? What would the answer be if I'm asking for enthalpy change instead? Okay, good, John, you got it. Enthalpy change, what would the answer be? Very good. It will be E2 minus E1, because enthalpy change is from reactant to where your product is. So the answer could be B. So your school can easily adapt this question, all right, and just change it up, right? They can just change, oh, I want the enthalpy change of the forward reaction. Then answer here would be E2 minus E1. Okay, of course, there's a bit more possibility. Let's try one more. What would answer be if I go with the activation energy for the reverse reaction? Listen carefully, activation energy for the reverse reaction. Hey, wow, you're smart. But I let the rest try first. Go and think, activation energy for the reverse reaction. Okay, so for the reverse reaction, instead of Mn to P, is P to Mn. So P to Mn, the height of the mountain you have to climb, is E3 minus E1. So the new answer would be C if you are looking at the activation energy for the reverse reaction. Okay, so is this going to be easy? Not the easiest if we decide to upgrade the question. Okay, but I'll say that this is a pretty good point for us to push on. Next to question 11. Okay, this is a very important question for us to attempt because this is one of the first few calculation question. Later on, I'll go through in detail how to do. Okay, this one, I'll give you 2 minutes to try. But before we try, I just want you to make sure we are clear with this. This is about enthalpy change is equals to BB minus BF. My laptop overheating. Okay, please go ahead and try. Okay, 1 more minute. Now, can do, cannot do, need more time. I see that majority of you haven't submitted your answer yet. Okay, we're gonna go through step by step. If you guys have a calculator with you, you can help me out. Okay, but I want to really run through properly on how we're supposed to do question 11. So as I was mentioning earlier, this is one of the most important questions today because what we're doing is we're doing a direct application of our BB minus BF formula, bond breaking minus bond forming. That is how you get your enthalpy change. Now, what do we break? Let's revise again. For bond breaking, we are always breaking the reactants, right? And when we are forming, you're always forming the product. So what we need to do is to first calculate the bond breaking. And how can we do so? The bond breaking can be calculated by exactly narrowing down what bonds we are breaking. So these are the first ones that we'll be tackling. We are looking at a total of 6 CH bonds. So I'll say times 6 CH. Let's not forget, there is still a CC single bond here. So we need to plus 1 times CC single bond plus finally the CL single bond. So what we're going to do here is to do 6 times. The CH here is 410. Do I care about the plus minus sign? Let's just ignore all of that. We just calculate the numerical value. Plus 350 plus 1 CC single bond plus 240. So how much would this give us? Let me just type it into my calculator. Oh my god, I typed 6. Okay. 6 times 410 plus 350 plus 240. The bond breaking adds up to 3050. Let's move on to the bond forming. What are we forming? We are forming all of the products, right? So let's take a look here. We are forming 1, 2, 3, 4, 5. 5 CH bonds. So I'll write that down. Maybe I'll give you a bit of a space. I'll write down a bit lower. So bond forming here is 5 times CH bond plus what else? Don't forget, there's a CC single bond here. So a CC single bond plus a CCl bond, CCl plus a HCl. So it's very close. You don't confuse yourself later on when you choose the values. So let's start with the 5. So for bond forming, we got 5 times CH. CH is 410. CC single bond is 350. CCl is 340. Oh, handwriting cannot make it. HCl here is 430. So we'll take out the calculator and then we'll start typing. 5 times 410 plus 350 plus 340 plus 430. You should get 3170 joules. So we can just now put it back into the formula because we know that is BB minus BF. BB is 3050 minus your bond forming, which is 3170. Okay, so when you take 3050 minus 3170, you end up with negative 120 kilojoules per mole. So that's why the answer here is B. Yeah. Okay, I'll zoom in again in case any of y'all need the working. But this is legit how you'll be doing it in the exam. You break off your reactants, you form all of your products. Just take the bond breaking value minus the bond forming value. You end up with your answer. Okay, I feel like when I was looking at the chat, not many of you actually sent in your answers or you were uncertain if it's correct. So I want you to take this chance to double check to make sure that you are clear on how to do it. The next time when you see this question again, I want you to nail it down. There's another more difficult format to this question, which is they give you the enthalpy change, but they make one of the bond energy an unknown value and they ask you to solve for it. It's pretty much just math at that point, right? Because you know how much the enthalpy change is, but you do not know one of the values. You let it be x, and then you solve for x. So that could be another way the question is set. Okay, you want me to teach you a secret hack? It's like secret hack, okay? It's not really a secret. The secret is you need to read the question. The question already tell you this is an exothermic reaction. Exothermic will always be negative enthalpy change. You don't go and freaking choose C or D anymore. C and D are endothermic. Correct? So there's no reason why you end up with C or D. That's just being foolish. Okay? So whether you calculate correct or wrong, that one, sure, maybe some of you cannot calculate, right? You get N of A. But at least you shouldn't be choosing C or D. Okay, otherwise I'll move on to one of the last few questions for today already. Let's take a look at question 12 next. Okay, we'll take a look at question 12 and I'll briefly do question 13 as well. The remaining questions, feel free to actually attempt them on your own. I always tell you, all right, I like to include a bit more questions so you can continue practicing because the answers are provided for you. This one, I'll just give you a minute. If you know, you know. If you don't know, it's going to be wrong. Hey, nice. Okay. Yuying, suspicious. Okay, answer here is B. Yeah. Let's go stage by stage. From solid to liquid stage, what is this? It's melting, right? So is melting exo or endo? Melting is actually endothermic. Right, so I write that down. Melting, endo. Okay, so cannot be stage 1. From liquid to gas, ne? Okay, so liquid to gas, it's boiling. Boiling is endo as well. Let's continue. From here to here, what is this process called? It's combustion, right? So combustion is definitely heat energy release. We're looking at exothermic. Next, here from gas to liquid is condensation. Condensation, it's exothermic, which is why answer here is B. Right, we're looking at exothermic reactions. Okay, now I want to bring everybody's attention to part A over here. I think this is really important for us to take note because, sorry, it's a bit of a lagging. Over here is really important because this is an important, write it down with me, answering technique. I mean, of course, if you have the curated notes, you can find the answering technique in the curated notes. But when we're talking about exothermic reaction, enthalpy change is BB minus BF. An exothermic reaction implies we are looking at a negative enthalpy change, which means your bond forming must be a bigger value than your bond breaking. So take a look here. The energy released during bond forming is more or greater than the energy absorbed during bond breaking. This is literally what they're looking at in terms of bond breaking and bond forming. They want you to tell us that the bond forming is bigger than bond breaking. But we do not use the word energy required, right, for bond forming or bond breaking. We use the keyword here, energy release during bond forming, energy absorbed during bond breaking. The reason why we say energy release is because we are looking at an exothermic reaction. Energy absorbed here is because we are looking at an endothermic reaction. So the keywords here are important, which is why this question is a very heavy answering technique basis. This is the correct way to be answering it. Okay, if you know what are your reactants and product, you're supposed to say energy release during the bond forming of blah 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 is more than the energy absorbed for the bond breaking of blah blah blah. But because this is a generic question, you do not need to mention the specific reactants or products. Okay, so this one here is about how you answer. If you answer it in the correct way, given the format here, you will have a much higher chance of scoring. Otherwise, your teacher need to be looking at ways to give you the answer. Okay, I'll end off with this question today. All right, instead of getting you to do the calculation, I would like to impart you with a little bit of extra knowledge. Okay, now let me go through the traditional way of solving this. The traditional way, as we have talked about earlier, was to go and count how many CH bonds we break. Can see 5 CH bonds. Can see 410. So 5 of them. Then after that, I go and see, okay, I have a CC single bond, right? So that's under bond breaking. Then I have a CBr bond. CBr is 280. Let's not forget, there is still the BR bond, 193, right? Then the traditional way is to go over to the product and go like, okay, I have 4 CH bonds. Okay, I still have my CC single bond. Okay, my CBr now I have 2 of them. So 2 times 280, and I have a HBr bond. You do a BB minus BF, you will get your answer. So this is the best way to do it. This is how you should start off learning. But now I want to just leave you with this thought. You decide whether you want to do my method or the traditional method. Okay, up to you. Both are correct. Now, if you agree with me, you compare before and after, spot the difference. Do you agree with me that actually this part that I'm highlighting here is exactly the same? So if you're gonna break it and then proceed to form it, you can expect that the values to be exactly the same. So what I'm trying to get you to do here is a shortcut, meaning the bond that we really need to compare before and after, what we actually need to break, not break and form, we need to completely break this CH and this BR. While what we need to form is this CBr and this HBr. In other words, I can simply shortcut this by saying that CH is 410, BR is 193. So if we add this up, it will be 603. And this is for my bond breaking. What about for my bond forming? My bond forming, I need to form the CBr, which is 280, form the HBr, which is 366. Ah, shit, my brain cannot take it. I need my calculator. Hey, that's what happens when you grow older, okay? It's normal, okay? I can't do mental stuff anymore. 640. Which means if you want to do the enthalpy change, equals to BB minus BF, 603 minus 646. 606 minus 606. You get a minus, did I type wrongly? 603 minus 646. You get the beautiful negative 43, which is exactly the same as the answer. So what I'm telling you is I would strongly encourage you to stick with the traditional method if you're not confident. You break everything, add it up. You form everything, you add it up, you just BB minus BF. Right, that will give you the answer. 100%. It's correct and it's the usual way of doing it. My way of doing it, or when I'm checking, I'm smart enough to realize that there are certain bonds that were untouched. So if I'm going to break it and I'm going to form it again, those values more or less cancel out each other. So I only focus on the yellow part, the bonds that are uniquely broken and uniquely formed. And that will get us the same answer as well. So I'll leave this option to you. Typically for my own students, I will teach them that you use the first traditional method to do your calculation. And when you're checking, you use the second method to check. That way, if both answer matches, you know for guarantee, your answer is definitely correct. Okay, so I thought that it would be nice for me to leave you with this because not a lot of school teachers will be teaching you this way of solving it. All right, now, of course, there's a lot more questions that you can go and try by yourself. A lot of them are structured questions, a lot of calculation questions as well. Another one of the answering technique that you can go and read through. So even if you don't have the time to fully do everything, what I suggest is you can read through the answer sheet. At least that gives you a certain level of exposure to the questions. So every single lesson will be preparing a new worksheet. So I think it's really good for you if the topic is something that you're not good with or not confident. If you cannot attend the lesson, you can watch the recording or at minimum, look through the worksheet with the solution. Okay, and I think that would be a very good place for you to brush up on your weaker topics. All right, and I think with that, I'll come to the end of today's session. So I hope you guys learned something new about energy changes or refresh whatever you have learned in school. That's about it. Bye, people, and you have a good rest. Gwen, the correct answer to your question is that it's better to think of it as no general trend because it depends on the bond that we are breaking and forming. Okay,